Our final subject in applications of integration is to revisit differential equations. You might wonder why we would use integration when looking at differential equations. It turns out that integration is a key technique for solving differential equations. In order to see this, let's recall Newton's law of cooling. This said that if you have a hot object in a cool room, it will cool according to the difference in temperature between the object and its environment. So here, τ is the characteristic timescale of the system, and Tn is the environment temperature. Now we saw before that once given a solution, we can see it's a solution by substituting it into the differential equation. What we want to do is to try and integrate this equation to find the general solution to it. Let's see how to do this. This is actually what's called a first-order linear separable equation, and these are particularly easy to solve because we can rearrange them and integrate. But we rearrange them using the idea of differentials. So we rewrite it in the following way. We divide through by T minus Tn. Now what we want to do is to find temperature as a function of time. So what I've done is on the left-hand side, I've taken all of the parts of the equation which involve the temperature. And on the right-hand side, I've put everything else, which in this case is just a constant. Now what I'm going to do is use the idea of differentials and multiply through by dt, where I mean little t, the time. And then what I can effectively do is think of this temperature, the change in temperature with respect to time times its differential little dt. I can effectively cancel those out, just as if I was doing a change of variables. And then what I have is as follows. Now writing it in this way using differentials mean that I can actually now just stick on integration symbols and integrate both sides of this equation. So this equation now makes sense as one integral on the left-hand side equals another integral on the right-hand side. We need some limits to the integration. One could just integrate this and have an arbitrary constant and then find that constant later. But if we know the initial conditions, we can actually put those into the integration limits now. So what I say is that at some time t0, I integrate up to some later time t, and in that time we go from an initial temperature up to whatever final temperature that we want, which will be our function of time. So now we can go ahead and integrate. On the left-hand side, I'm integrating with respect to capital T, remembering that Tn is just a constant. So this gives me the log of the temperature difference. I'm assuming that temperature is hotter than the environment here. And on the right-hand side, I'm just integrating a constant, so that just becomes minus 1 over τ times t evaluated between t and t0. So putting in the limits gives me this equation. Collecting the terms in the logarithm and then taking the exponential of both sides, this leaves me with, which is the solution that we had last time. Now we know that there's a constant of integration here which I've absorbed into the initial temperature of the system. The other first order separable equation that we investigated before was the logistic equation, which tells us about population growth subject to a carrying capacity of the population. We can actually integrate this in the same way, although it's a little bit more complicated integrals that come out. Let's have a go at this just now. So we have our logistic equation. The change in population is equal to k, a constant, times a population, times 1 minus p over k, where k is the carrying capacity. Now we integrate this using the separation of variables technique we used before, which means we move everything involving p onto the left-hand side and everything else onto the right. Now I'm going to multiply through by dt, and at this stage I'm going to add on integration symbols. Again, instead of having a constant of integration once we've done the integral, I'm going to absorb that into the limits of integration right now by using appropriate initial conditions. So at t0, I'm going to set the population equal to p0. I'll integrate up to a later time t, at which time the population is p. The left-hand side integral isn't quite so easy to do. What we need to do is we need to note this relationship you can check by gathering the denominators on the right-hand side and seeing that it equals the left-hand side. This step to go from the left to the right is known as partial fractions. We're not going to study this in this course, but in order to see that this is correct, it's relatively straightforward to manipulate the right-hand side to get the left-hand side. Then using this, the integral now becomes. So integrating and putting in the limits, I have the log between p and p0, which using the rules of logs, I can write as the log of p over p naught. Similarly, the second term, I can write like so, and this is k times t minus t naught. Combining the logs and taking the exponential of both sides gives us the general solution. So integration can be used to find the solutions of some differential equations. What we've looked at is separable first-order differential equations. We also looked at the problem of a mass on a spring, which gave rise to the simple harmonic oscillator equation, a second-order linear differential equation. How do we go about solving that? Well, usually you would do trial solutions for that, but actually you can integrate a second-order linear differential equation as follows. We'll have a look at this even though it's not examinable for the course, but it's instructive to see how to integrate something a little bit more complicated. Let's begin by writing down a general second-order homogeneous linear differential equation. So here's a general second-order linear homogeneous differential equation with constant coefficients a, b, and c, and I'm going to have a go at solving this by direct integration. In fact, the constant a we can just scale out of any problem, so I'm just going to get rid of it. How do we go about integrating this? What I'm going to do is use a differential operator notation, and I'm going to write down an equivalent differential equation as follows. So let me assume there's constants alpha and beta, such that I can write down this equation where the parts in brackets dB dx minus alpha and dB dx minus beta I consider operators in the sense that they operate on everything to the right. So that means if I multiply stuff out in the usual way, so this equation then is the same as I started with, but with just different constants. Now the question is, can we integrate the equation in this form? Let's let z of x be an auxiliary function, which is dB dx minus beta acting on the function y. That means dz by dx is alpha times z. We can integrate this using separation of variables. So z is equal to a constant a times e to the alpha x. A is a constant of integration, indicating that I've done one integration on the differential equation. So then I'm left with a linear equation for y, which is now first order. dB dx of y minus alpha y is equal to a e to the alpha x. Now, I need to go about solving this. I can't use a separation of variable technique just yet, but what I can do is notice the following trick. Let me consider a seemingly unrelated thing. Y times e to the minus beta x, and I'm going to differentiate that using the product rule, remembering that y is a function of x. Then this becomes e to the minus beta x times the left-hand side of the differential equation I want to solve. So therefore this is equal to, and so what I've shown here then is I can write the first order linear differential equation for y, which has the constant a in it to indicate I've integrated it once, in the following way. And I've actually now turned this into what's called a separable differential equation that we were just looking at. I have the total derivative of something on the left is equal to a function of x on the right. So I can now integrate. Integrating this then gives me y e to the minus beta x, which is equal to a over alpha minus beta, e to the alpha minus beta x, plus a new constant b. So I've now got two integration constants, a and b, which indicate that I've integrated a second order differential equation. Each time I integrate, I get another integration constant. Multiplying through by e to the beta x, I get a constant times e to the alpha x plus another constant times e to the beta x. Now where do the sines and cosines come in which give us an oscillating spring or an oscillating harmonic oscillator? Well, for that we need to wait for the next part of the course where we study complex numbers, which actually link the exponential functions and the sinusoidal functions in a very profound way.